Okay, so in this video now we will define what static equilibrium is. We look at the conditions of static equilibrium, and then we'll solve a simple problem where we'll use all the ideas. Okay. Now when we did Newton's laws of motion, you came across something called equilibrium. Okay. The equilibrium there was not necessarily static. So one of the conditions that we understand for an object to be in equilibrium is clearly that the result of all the forces on the object should be equal to zero. So we know that the net forces on all the object, okay, the sum of all the forces on the object should be equal to zero. Now, in order for the object to also be static, where it's absolutely not moving, okay, we have another condition, which is essentially that the net torque, tau net, on the object also be equal to zero. Okay, now the first of these equations also ends up giving us two equations in two dimensions, which essentially says that the summation of all the forces along the x direction is zero, and then summation of all the forces along the y direction is also equal to zero. Okay, and we'll see that the torque being equal to zero also gives us a freedom, not necessarily in the sense that it gives us, in various directions, but we can choose the torque about different pivot points and obtain several equations. So the example that we will do, the first example itself, will clarify these ideas, and you should be on your way to calculating conditions for static equilibrium. All right, so let's look at the very first example. So in this example, what we have is, let's say that I have a wall on one side and let's say a ceiling on the other side, and let's take some kind of a bar that is supported out here. Okay, the mass of this bar is L, and let us say that the length of this bar is L. Okay, and let us say that we have a string that points in this direction, okay, and it makes an angle, let us say it makes an angle theta with the vertical, okay, and our goal is to calculate a few things. We want to know the tension in this string, okay, then we also want to find the horizontal and vertical forces at the hinge. Okay, so at this hinge, we want to know, at this point, we would like to figure out what fx and fy are. So let's call this guy fx, let's call this guy fy, and those are our goals. Okay, so we're going to employ ideas from torques as well as forces and solve these things out. Okay, so obviously the first thing that you should always do in these cases is draw a free body diagram. Right? So let's go ahead and do this. Now, what we'll do is I will still draw this object as an extended object. And if we look at the forces that are acting on this object, we have the tension pointing in this direction. Okay, we'll assume Fy to be up, Fx to be to the right. Although we don't know these directions in the beginning, we'll just assume these to be the cases, and if we end up getting a negative value for Fx or Fy, it would simply mean that they're pointing in the opposite direction. Alright, so we have that. Now also we have the force of gravity. Now this is where we just need to understand a few things. We're assuming that this rod is uniform. We're saying that this is a uniform rod. Okay, so if that is the case, then the force of gravity on this rod will be acting, obviously at each portion of the rod, but for all our purposes, for calculational stuff, we'll say that this force will be acting at a point called the center of mass or center of gravity of this rod. Okay, so we will show that this force is simply pointing out here. Now in one of the future videos we'll actually learn how to calculate center of gravity and center of masses, and I apologize for this, the order to be kind of messed up, but just how it is right now. So we have all these forces, and our goal is obviously to figure out the resultant, basically to figure out T, Fx and Fy. Also we know that the angle is theta out here. So let's go ahead and let us look at all our conditions. So the first thing we know is that what we'd like to do, actually let's do that. What we'd like to do is break t into components. Okay, so let us find the horizontal and vertical component of t. Now, if you notice the way the angle theta is given, okay, the vertical component happens to be the adjacent side of the right angle triangle, and therefore the vertical component is t cosine of theta, and the horizontal component, which happens to be the opposite side of the triangle, is equal, or opposite to the angle theta, it ends up being equal to t sine of theta. Alright, so we have all our things, and this would make life easy in calculating stuff. Okay, the first thing we'll do is obviously we'll take, let's say take summation of fx is equal to 0, all the forces along the x direction. Okay, in the picture, if you notice, there are only two forces acting along the x direction, the fx and t sine theta, and the way we've drawn them, at least the way we've drawn fx, these two are opposite each other. So we have the condition fx minus t sine of theta is equal to 0. So this gives us one equation. Also, the net force along the y direction is 0. Okay, and if you look at this picture, we have Fy and t cosine theta pointing up, and we have mg pointing down. So we have Fy plus t cosine of theta is equal to mg. Okay, the first equation I could have written fx equals t sine theta. It really, doesn't make much of a difference. Now, I have these two conditions, but we obviously have three variables, three unknowns rather, and so we need a third equation. Okay, and this is where we'll go to torques. We'll take the torques about certain points, and we'll try to figure it out. So here we'll take, say, the net torque being equal to 0. Okay, now what we understand is that since the object is not rotating, it is not rotating about any point. Okay, so this allows us to use any point as our pivot. Okay, and for convenience, you choose points such that it actually minimizes the number of forces that you have to deal with. So in this case, if I were to take, say this as point A, okay, let's say I'm going to call with the center of mass as point B, and then the other end as point C. Okay, if I were to take torques about point A, okay, you notice that fx, fy, and this t sine theta, they all give us 0 torques. Right. On the other hand, if I were to take torques about B, I would still have to worry about Fy. Okay. Actually, about B also, Fx, T sine theta, and mg gives us 0 torque. And then if I were to take torques about C, then T cosine T sine, which is basically T, ends up giving, and Fx also ends up giving us 0 torques. Now, since we are looking for T, Fx, and Fy, I think A ends up becoming the best point to take the torque about. And what it does is it gets rid of fx and fy, and then we can solve the problem, and also t sine theta. So let's calculate the torque about point A. So let's do this about A. And once again, you could choose any other point. It really doesn't make any difference. Obviously, my goal is to make life as simple as possible for calculational purposes. So if I were to take torques about A, clearly we see that fx, fy, and t sine theta give us 0 torque. The only two forces that give any torque are t cosine theta and mg. And if you were to look at it, t cosine theta causes a counterclockwise rotation, and mg will produce a clockwise rotation about point A. So my net torque will end up being t cosine of theta times, it is a distance L from the end, minus mg times L divided by 2, and all this is equal to 0. Right away, I can solve for t, and this gives me t is equal to mg divided by L times cosine of theta. And once I have t, I am now ready to calculate each of my individual things. Okay, fx. So therefore fx now is which is simply equal to t sine theta is simply equal to mg over L times sine theta over cosine theta. So I can write that as tangent of theta, and then I can also get fy, and then therefore fy is equal to mg minus what is it, t cosine of theta. So T, which is mg over L. Oh, I think I made a mistake here. This is mg over 2 cosine of theta, not L. And this is equal to mg over 2. And then this is also equal to mg over 2 times, what was T, mg, yeah. So this was equal to cosine of theta times cosine of theta here. And this ends up giving me simply mg divided by 2. Okay, so we have all our forces, and we also chose the correct directions for the two forces about the hinges, and so everything else works out really well. Okay, so this is a simple way of taking care of the problem. There is the math there's a little bit of algebra at the end, but just take talks about appropriate points and everything will be good.